we would like to analyze the expected time it takes for searching in a hash table when we resolve collisions using open addressing. So a quick reminder of what expected values actually are. So expected values are relevant in the setting of random variables. So if we, for instance, throw a die, so a random variable might be the result of throwing a die, then the expected value is essentially the average value that we would get, and that can be calculated by taking each of the possible values and multiplying them with the probability of them occurring. So with a probability 1/6, I will throw a 1 if I have a fair die, with a probability 1/6 a 2, and so on. If I now do the calculation, this is 21 divided by 6, so that's 3.5. So on average I will get a 3.5 in this setting. The general formula that we are applying here is that we're summing over possible values I, multiplying them with the probability that the random variable actually is I. We can reformulate this, and this we will be using to analyze the expected number of probes that we need when we search. So we can reformulate this by writing this as a sum of the probabilities that x is at least I. So you see the I disappeared in the sum. Instead we are having the probabilities that x is at least I. And if you do the calculations in this example, the probability that I have at least a 1 is 1, because I always have at least a 1. The probabilities that I have at least a 2 is 5 divided by 6, so that excludes the case of throwing a 1, and then 4 divided by 6, and so on, down to 1 divided by 6. So 1 divided by 6 is a probability that I throw at least a 6, which is essentially saying I'm throwing a 6. And if you do the calculations, of course you get the same value as before, 3.5. So now back to hashing. So we want to analyze the number of probes that we do when searching, and let's assume we're doing an unsuccessful search. So the expected number of probes we will rewrite as the probability, the sum over the probabilities that the probe that I do at least I probes. So I always do at least one probe, but let's think of this a bit more. So the probability that I do at least I probes, so the probability that I do at least 2 probes is the probability that the first probe actually tested a slot where there was an element. So if I assume that I picked a random slot, then this would be n divided by m, so the number of elements divided by the number of slots. So that's the probability that with my first probe, if I probe a random slot, that I actually hit a slot which already contains an element. So in that case, I will have to do another probe. So now the probability that I, for instance, have at least 3 probes is the probability that I, in the first time, hit a slot with a non-empty element, but also the second time. And the second time, so for the second slot that I hit, then there are m-1 remaining slots, and there are n-1 remaining elements that could be in that slot. And this product continues down to, so the probability that I have at least I probes is the probability that the first I-1 probes hit a slot with an element. So this then goes down to n-I plus 2 divided by m-I plus 2. Now all of these factors I can actually simply bound by n divided by m. This simplifies this product, or it gives me a simple upper bound of n divided by m to the, and the number of factors is I minus 1. N divided by m, that's our load factor. So what we have here is actually the load factor to the I minus 1. So that's a probability that we're doing at least I probes. Now I wanted to calculate the expected number of probes. If I now plug in what we calculated here, then the expected number of probes is actually upper bounded by alpha, by the sum up to n alpha to the I minus 1, which I can rewrite, or no, which I can upper bound by the sum going up to infinity. And now I simply have the geometric sum. The geometric sum in its limit, if the base here is alpha, is 1 divided by 1 minus alpha. So 1 divided by 1 minus alpha is the expected number of probes for an unsuccessful search, which means that as long as the load factor is not close to 1, this expected value will be some kind of constant. So if the load factor is, for instance, 1/2, the expected number of probes is 1 divided by 1 minus 1/2, so that's 1 divided by 1/2, that's 2. But if alpha is very close to 1, this expected number will increase dramatically. So if my hash table is, for instance, full up to 1 or 2 elements, the expected number of probes will be very high.